All right, this is part 2 of 2 on the lecture covering the material from chapter 1 of your textbook on bias in the scientific method. Let's jump right into the next slide. So, in the last section, we were talking about how we develop theories and the characteristics of theories. And in this section, I want to talk a little bit about how we go from a theory, which, usually involves hypothetical constructs or concepts, how we get from that theory to a testable hypothesis that we can actually then conduct an experiment to examine. So we were going to define a theory as a coherent set of propositions that are used as principles to describe, understand, and explain psychological or behavioral phenomena. So these long definitions with a fair amount of technical terms in it, I like to sort of break down piece by piece. First and foremost, a coherent set of propositions. Okay. So by coherent, we mean that logically these propositions hang together. They make sense in a reasonable fashion as you walk through the theory. They're connected in a variety of ways. So in that sense, they're coherent. And by propositions, things that you're proposing to resemble the truth. But ultimately, what we're really saying in most propositions is something akin to an if-then statement. And we use them as principles to, again, address the 4 goals of science that we discussed in previous slides: describe, understand, explain, and of course sometimes control psychological or behavioral phenomena. So theories often address answers to how and why questions. Okay. Your theory has a profound impact on how you conduct your research. All aspects of your study, from the initial idea to how you interpret the results, everything from the beginning to the end, is informed by your theory. What you decide to study and how you decide to study it is heavily informed by the particular theory that you hold regarding that area that you're examining. The issue, though, is that we cannot directly test a theory. The reason being because theories often involve these hypothetical constructs, words like memory or aggression or development, and we have to define those words in these operational definitions, in these practical, objective ways where they can be measured. So we have to take a theory and from it derive what we call a testable hypothesis or a research question. And so the testable hypothesis we're going to define as a statement often in the form of a prediction that is made prior to the actual collection of data. So when I propose a hypothesis, I'm going to say something like, let's say that I had a theory. I come back to this example a lot because there's lots of research on it, but let's say I had a theory how gender is tied to verbal versus physical versus non-physical violence. Okay. So how gender is related to, I might have a theory that, male or female identification affects whether you're more or less likely to be physically or verbally violent in some form, or aggressive in some form. Basically, I could propose that as an if-then statement, a prediction. Based upon the theory that I hold, I could argue that men will score higher on levels of physical aggression and women will score higher on levels of verbal aggression. Okay, this is again just a theory that I'm throwing out there as an example. What I'm essentially able to do then is predict that based on the relationship between these 2 variables, this is how things are going to play out. And the hypothesis is usually phrased in terms of concrete data. So, gender is something I'm going to, ask the person to how they identify, and I'm going to establish that as a variable. That's an operationalization of a larger concept like gender, of course, which we know is much more complicated than binary. But ultimately, the idea being that we're going to assign a value or a label or some sort of self-identification from that person. We're going to enter that practically, objectively into our study, and then we're going to have we're not going to just grasp at the hypothetical construct of aggression. We're going to have to measure that some way in an objective way. So we're going to have to utilize some sort of measure or some sort of value that we're going to assign, probably numerically, right, in most cases, to the person's levels of verbal or physical aggression. It's really important that your testable hypothesis is it's hypothesis, singular, hypotheses, plural. It's really important that a hypothesis is made a priori, which is a Latin term that means before the study is conducted. It reduces the possibility of bias. If you generate your hypothesis post hoc, another Latin term, after the fact, right? After the study is complete, when not only have you conducted the study, but maybe you're even looking at the data, right? This tempts you to formulate a hypothesis that fits the outcome. Okay. Rather than formulating a hypothesis derived from your theory, you're now going to retrofit whatever you saw or observed, and you're going to form a hypothesis that fits with the data as opposed to hoping to find data that fits with the hypothesis. This is a very dangerous process, and it's one of the hard and fast golden rules of science. You have to form your hypotheses a priori. Okay. If you do them after the fact, then you are much more prone to introduce error and bias. We are motivated to find good results, and we like to think that our theories are accurate or they hold some water. And so if you conduct a study and it turns out that your experience is starting to show, or the data is starting to show, that that theory doesn't hold water very well, there is too much tendency as human beings to try and alter our perceptions, our hypotheses after the fact to kind of make them fit the data or fit the observation a little better. So it is sort of a rule that we try to stick to because it keeps us honest. Your book refers to variables as the language of research, and I think that's a good term for it because ultimately variables are a huge part of description and execution of a research study. So we're going to utilize the word variable in this way. Is right there, the root vary is in the word. It's essentially a characteristic that people vary on, whatever it is. It's not something where everyone has the exact same level of that thing. And this can be anything in the world of psychology research. It can be very practical and physiological. You could say, well, like height, for example, is a variable, right? Everyone, no one, not all people are exactly the same height. People have a varying in their heights across a certain range. Um, Something like people's memory, intelligence, these are all things in which we vary. So a variable, in order to be so, has to be able to take on different values. And if you look at your book, there's an example that I won't get into today where they talk about good examples of pulling variables out of theory by Kahneman and Tversky. That's in your textbook. Um, Variables are critical to research, especially the concept of independent and dependent variables. We're going to talk at great length throughout the course, especially when we talk about true experiments. We're going to talk about independent and dependent variables. What I want you to know for the purposes of this lecture is essentially they're often abbreviated IV, DV for independent and dependent variable, respectively. The independent variable is the element of the study, the variable that you as the researcher systematically manipulate, change, or select. So let me give you an example. Let's say that you had a new idea for how to treat people for depression. You had a new therapy approach in mind that was driven by your theory. You would develop this approach for therapy for depression. You might select a sample of participants that you're going to study, and what you would essentially do is one group of those people would get your new experimental research, and one group would get something else. They might get nothing, which we might call a control variable. They might get some alternative. They might get this sort of modern industry standard so that you can compare your new development to that typical way of doing things, the standard operating procedure kind of thing. But regardless, you're going to manipulate which level of that independent variable the participants receive. So they're going to get a different level of it depending on how they're assigned, and we'll talk about that as this goes on. But ultimately, what you need to know is that an independent variable, or an IV, is one that is manipulated by the researcher. The dependent variable is essentially your outcome. Independent, dependent. Dependent is dependent upon the manipulation of the independent variable. So the dependent variable can be thought of as the observed effect, the result, the outcome, and it's measured in response to some systematic change or variation in the independent variable. To keep using the same analogy, if the independent variable is you either get no treatment, you get the standard treatment, or you get my experimental treatment that I've developed, that's the independent variable being manipulated. The outcome might be some measure of level of depression. How are people doing? And did they vary or change systematically? In this same example, did people in my new treatment condition, did they show more improvement or less symptoms of depression? Are they rating their depression at lower levels compared to people in other independent variable levels, like other groups, like the standard treatment or the control? What you would want to see is that people at least consistently over time, statistically, got better in one group versus another, and then we'll talk about how you interpret that and try to make sense of it. So if I want to conduct a study, I need participants, right? And no matter what, if I'm doing any kind of research on humans or animals or whatever, I need some sort of participants to conduct the study. And we have two concepts that are interrelated that we really need to talk about in detail. And again, we will come back to this in subsequent chapters in the book. Sampling and populations, or we might think of it as samples and populations in this case. So when you observe, when you conduct a study, whenever you use your empirical method to look at something related to human behavior in psychology, we're collecting data from a sample. okay, from a group of people, a group of individuals, a group of subjects that represent a larger population, right? So if I'm interested in, people's levels of depression, I can't go out and test every human being on Earth or every American or even everyone in my town. It's just not feasible or practically possible to do that in most cases. So what I have to do is I have to pull a few people or a smaller number than the larger population that I'm going to use as a sample, but I'm going to do it in such a way, which again we'll discuss in a whole chapter on its own. I'm going to do it in such a way that I hope that that sample is representative of what the larger whole population looks like. So when I talk about a population in psychological research, what I'm referring to is this is the definition from your book, an entire collection of people, animals, plants, or things, all of which can be referred to as units from which you collect information as a researcher. Now that's very clinical and very scientifically cold, but people do various types of behavioral research on mice and on primates and things like that. If you're a botany researcher or a chemistry researcher, you might be utilizing plants. Whatever it is you're studying, if it's things, we might think about, if you're an atomic physics researcher, you might be utilizing atoms of a certain element. But whatever it is, all of those that exist is the population. And it doesn't have to be all human beings. You can be more specific. You can say, you know, um, all college students of a certain age, all people above a certain age, if you're studying geriatrics or elderly people. If you're doing developmental research, you can say children aged 0 to 18 months, but that is your larger population that you're interested in. The sample is simply a group of units selected from that larger population. So we use samples in order to collect data because the population is essentially, in most cases, too large to study in its entirety. Um, the problem, with that is that we don't always know if it is representative. So ideally, we want what's called maximized generalizability. We want to be able to generalize the findings with the sample as much as possible to the larger population. This goes all the way back to the first lecture when we talked about Newton's guidelines for science, right? Theories and scientific statements should be as universal as possible. We're trying to maximize generalizability. So we are very careful about how we select our sample. We look at the sample in various ways to test whether or not it's representative even before we might start gathering data. But ultimately, we're hoping that it reflects the larger population because that's what we're really interested in understanding, not just this small group of people we were able to draw into the study. However, the issue, of course, again, bias is the enemy of good science, right? So now we're faced with this idea of sample bias. There's a possibility that some members of the population are less likely than others to get selected to be included in your sample, and that introduces bias, which can lead to misleading results. If I go out and do a random sample of people in Blacksburg, and I'm interested in something about gender, right, and I just randomly select, by random chance, I could end up with predominantly people that identify as male or predominantly people that identify as female. And as a result, if I'm interested in that variable especially, but even if I'm not specifically looking at it, it could bias the outcome in some way, especially if that outcome is also somehow interrelated with the concept of gender. So you want your sample to be representative as much as possible. And again, there is a whole chapter we're going to discuss where we really get into detail about how you do that, methods and techniques for pulling a sample from a population. This is just a little diagram to sort of help understand this concept. If you look at essentially the sample being pulled from a population, we hope that it's generalizable, right? But sometimes we have to be cautious because sometimes we end up with a sample that doesn't represent, and we should especially be cautious if we are going to then generalize to a different population, right? A different type of individual, on some major variable. So, how do we evaluate evidence and theory in the scientific method? That's an important question, right? This is an epistemological question. How do we come to know things? So, part of what's required in the scientific method is that we collect observations of some type. And the word observation is being used very vaguely here, right? It's very general. Responses to question, test scores, rating, performances on a certain measure, reaction time, whatever it is we're looking at, right? We have to look at that collection of observations. And then once we have that group of observations, we have to categorize it, quantify it in some systematic fashion, and assign some numeric values that we either assign or they're computed in some way. Now, some variables, some outcomes we look at are pretty straightforward, right? If you want to see how quickly someone can complete a cognitive test, then you just time them, and the number of seconds or minutes that it takes them is essentially already a numerical value we can utilize. But sometimes we have to take a more vague concept or construct, a hypothetical construct, and convert it into some operational definition that we can then assign a value or measure some sort of value artificially. These numeric values that we have essentially constitute the data. And that's our empirical evidence. We're going to utilize those numerical values in our analysis, and we're going to connect that back from the hypothesis and the results to theory at some point. Right? We're going to talk in larger terms. We're going to generalize. Statistics, of course, are utilized to analyze these relationships among these objective, quantifiable measures of variables that are derived through our experimentation. So we can't analyze a statistical relationship between constructs, right? We can't take this the sort of the form, if you will, to borrow from Plato. We can't really measure a statistical relationship between gender and aggression as constructs, but we can ask people how they identify, assign that some sort of, albeit arbitrary numerical value, plug that into a statistical test, and then compare it to how they performed numerically on some test of aggression, for example, and we can look at how those things are related. And that's what we do in terms of statistical analysis. And what we're looking at eventually, what we're going to ask ourselves as we look at the data, in light of what we're seeing, in light of any systematic relationships that play out, what is the probability that the obtained results are due to chance? I want to take a moment to sit with this idea. We're going to come back to it multiple times throughout the class. I know I'm saying that a lot today, but this chapter really sets up where we're going from here for the rest of the course. What you're really saying is, okay, maybe I observe a relationship of one type or another. Maybe it does appear that, in my previous example, people that identify as women are more prone to verbal aggression, but less prone to physical aggression compared to those that identify as male. It is possible that that's a real relationship, that I'm really touching in on something that actually exists out there in the world that's meaningful. Or just by virtue of error and bias of some form that I may not be aware of, I may have ended up with a sample that just by chance showed that relationship. So we utilize statistical tests to figure out how likely is it that what we found is just due to chance. And if that number is quite low, for example, 5%, if there's a 5% chance that what we're seeing is just due to chance, then we say, well, then there's a decent chance, right, that what we're seeing is due to the predicted relationship, the hypothesis that I derived from my theory, that's the reason why I found these results, and that means the hypothesis is likely true. And I'm going to put the word true in air quotes here because we're going to talk about that later too. All right, I want to move on to two very important concepts in this class. I touched on them a little bit in previous talks that we've done or on previous lectures, but we're going to, again, explore these in a lot of detail. There are various subtypes of all of these, and we'll get into them. But reliability and validity are two very important standards for judging the quality of a research approach. Okay. The word reliability is synonymous with consistency. A reliable study produces data that can be replicated, repeated in another study, meaning that that study consistently, people who then come along and replicate that study and do the same research with a different sample are very likely to see the same results. It's reliable, it's consistent. You can rely on it to happen consistently. Validity is a different but related concept, right? Validity is the extent to which the study provides a true measure of what it is meant to investigate. So reliability is only about being consistent, not about being accurate. Validity you might think about as really being synonymous with accuracy. And I'm going to give you a very straightforward example, or a couple of examples I think that we could talk about that would make sense. If I have like a bathroom scale, right, and I weigh myself on that bathroom scale every day, that scale is valid, accurate, if it's accurately showing my real weight, what I actually weigh, right? If I then went to a number of other scales, especially those that have been, really carefully calibrated, would I get a similar weight at that same moment in time? If I stepped off that scale and onto some, super physics scale from the labs, would it show me the same number, right? How valid is my study in terms of it's actually measuring what it purports to measure, how accurate? Reliability is the idea, does it consistently weigh? So let's say that my weight is staying steady at 200 pounds, for example, right? And when I step on that scale, and I actually know in some objective way, I'm 100% aware that I do weigh 200 pounds, and I step on that scale, does it reliably show me 200? Or some days does it show me 205? Some days does it show me 195? Right? Is it consistent in its measurement? A poorly calibrated instrument an instrument that's not accurate enough can really lead to inconsistent results. The interesting thing about that, if you think about it, is a study can be reliable but not valid. So let's say that I'm studying aggression, but I have operationalized my definition really poorly, and what I'm really studying is people's extroversion, right? How outgoing they are. That study would not be considered valid. But if I was reliably getting the same measures, even though I was inaccurately measuring my construct of aggression, if I reliably got good measures of, something like people's extroversion, it could still be reliable. In our example of the scale, you could have a scale that is reliable but not valid, right? It always weighs 5 pounds too high. That's a reliable scale, but it's not valid. It's not accurately measuring my weight. I could have a scale that accurately measured my weight but was unreliable. So some days it would be right on, and other days it would not. A valid scale is one that is giving me an accurate measure, though, okay, and does so reliably. That's what we're looking for. Um, when we talk about reliability and validity, we also have to address the concept of confounds. Confounds are essentially unwanted sources of influence that can be viewed as viable alternative explanations for the results of the study. If you go back a little bit, when we talked about John Stuart Mill and his three foundational things you need to talk about causality: covariation, precedence in time, and then, well, the cause has to precede the effect, excuse me. And then finally, elimination of alternative explanations. Well, confounds are basically representative of those alternative explanations. It's another thing that you become aware of that could explain your results besides your manipulation of the independent variable. So confounds essentially reduce the validity of the study, and let's sit with that for a moment. If there are confounds in your study, then it turns out that you're not actually measuring only what you set out to investigate. There's something else that's influencing the outcome that you're not measuring or is not captured by your hypothesis or your theory even. A control variable is an attempt to try and measure those unwanted sources of influence. You're trying to essentially control for the influence of that confound. You're trying to make sure you measure things that could invalidate the conclusions. And in some cases, what we do is we introduce a control variable to eliminate that the confound is the responsible one for the outcome. Because if we measure it, or if we somehow balance it out throughout our conditions in our study, then we can remove its influence. So sometimes we do that just by making sure that it's accounted for in our design, and we'll get into that in detail. But other times you just want to be able to measure it and say, look, no, I measured that, and it has no relationship. It's not systematically changing the outcome, therefore I controlled for it. Or sometimes what you can do, if it is if it is influencing the outcome, excuse me, you can statistically pull that influence out in your data analysis to account for it. So there's lots of ways that if we identify a confound, we can do something about it. If we fail to identify it until after the study is done, or even worse, if someone who's reviewing the study finds it and we didn't see it, we then really can't do anything about it besides maybe go in and try and explain it looking at the data in various ways, but we can no longer control for it. We've already missed it. Again, keep in mind that a reliable study may not necessarily be valid, but a valid study has to be reliable. And this goes back to what I was talking about with the scale. Try to imagine a scale that is valid but not reliable. If it's accurately measuring your weight, then it's going to do so consistently. Okay. If today I weigh 195 pounds, it's going to show me 195 pounds. If tomorrow I weigh 205 pounds, it's going to show me 205 pounds. It's reliable, it's consistent, and it's valid. So that may have been a little confusing, so I want to make sure that I'm really clear on that. You can have a reliable study, but it may not necessarily be valid. I could be really accurately and in a very elegant way measuring the wrong variable, right? That doesn't really reflect what it is I say I'm trying to investigate. But I could do it in a reliable fashion, but the opposite is not true. This is simply a diagram to kind of give you a visual representation of what I'm talking about in terms of the relationship between independent and dependent variables, and then possible confounds or confounding factors as they're listed here. This is from your book. But essentially, in your top left corner of this triangle, you have your independent variable, which is manipulated. And then you want to see its influence on your dependent variable in the top right corner, which you can think of as your measured effect or your outcome. Notice that the two arrows extending from confounds can affect your independent variable manipulation. They can affect the dependent variable. They can have various ways in which they interfere with you accurately measuring this relationship. And a control variable is introduced to try and account for that confound in some way, or to control for it, to remove its influence from the measured relationship. Okay, let's shift gears here for a moment and talk a little bit about um, the importance of the role that science plays in society and how it can be misapplied in the form of pseudoscience. There's a really wonderful section of your book in this chapter where they talk about Kelly MacDonald et al.'s research. Oh, by the way, when I say, I don't know if everyone's familiar with this, just in case, if there is a journal article that is written by 3 or more authors, a lot of times we'll informally refer to it as the first person's name et al., which is an abbreviated Latin term, and others. Or you may say and colleagues in this case, but if I say MacDonald et al. Or whatever, then I'm referring to the group of researchers. It's just a shorthand. When you're writing like an APA, publication manual compliant article, what you typically do is you list all the names the first time, and then subsequently you can just say et al. As long as you have that year to designate which article you're talking about. Just a little aside there. But anyway, their research is covered in the book. And they talk about the idea of neuromyths, and these are persistent misconceptions, misunderstandings, misreadings of scientifically established facts, especially in brain research, in education, or other contexts. In the book, there is a link actually about these common myths regarding how the human brain works. I would really recommend that you check that out. There's actually a quiz that it'll take you to that you can conduct. Maybe we'll try that during the class meeting. I might pull that up. But ultimately, one of the things we talked about, the reason why it's important to study empiricism, we discussed a few reasons why I think it's important. And the last thing we discussed was about being consumers of research. And ultimately, it is so important that now more than ever that you're able to differentiate pseudoscience from science. What I mean by pseudoscience, pseudoscience is something that is presented in a way that sounds scientific, right? It might utilize a variety of terms, and we're going to have a whole slide coming up on the next slide about recognizing it when you see it. But pseudoscience is often presented in a way that looks, walks, and talks like science. If scientific method isn't epistemology, remember we said it's a way of knowing about the world, there are other epistemologies, right? We've talked about logic, authority, intuition, anecdote. This is another way of understanding the world, but unfortunately it's easily confused with real science. One example we can think of pseudoscience that persists is astrology, and that utilizes horoscopes to predict personality and behavior. There's no scientific evidence or proof to support astrology or astrological thinking. That doesn't mean it's not fun. Some people don't enjoy it, as a way of sort of characterizing personalities, or just, reading their horoscope and using that as some sort of, subjective test to think about how they're feeling about their lives. But presenting it as facts based upon the movement of the planets, for example, is a really good example of pseudoscience. And it has kind of fallen out of favor to some extent there, but of course we're seeing the rise of a lot of other forms of pseudoscience at the moment. And I do think it's really important that you as consumers know what it is when you see it. So let's move on to the next slide where we talk about how you do that. So this is from Lilienfeld, 2005. These were some warning signs for pseudoscience that they discovered by reviewing things in the media and in the culture. Be aware of a tendency for loopholes that limit the ability to falsify the claim. This is a really important bullet. I'm glad this is the first one on here. Remember we talked about a definition of science in the first lecture, and we talked about Popper's, they call demarcation criteria, right? But what really Popper's theory is the falsifiability of theory, of scientific theories or scientific propositions. If you are going to state something as a scientific fact or a finding, it has to be able to be falsified. When you are presented with something that may be pseudoscience, what you find is as soon as you try to question the claim or question the validity, the accuracy of what the person is saying, they introduce loopholes that, no, you can't actually explain it that way because XYZ, right? So this idea to constantly be adding these sort of post hoc loopholes that make it so you can't falsify the claim. One thing that defines or differentiates pseudoscience from science is that it's not self-correcting. One of the beautiful things about science is that it is designed to be a self-correcting system. That is the whole idea behind replication. Just because I found a certain finding in a study, until multiple researchers under different conditions utilizing similar techniques have found the same thing over and over and over consistently, reliably, we really can't speak too much about whether or not we have a good handle on what the likely truth is, or something close to truth at least. Um, that self-correcting process is very important in the way science goes forward. If you think about the early stages of certain sciences, think about the treatments for cancer, for example. Early chemotherapies versus today's targeted chemotherapies are worlds apart, right? And the reason why that is because there was new technological developments. Those new developments were tested scientifically against the old ones, and they were found to be much safer and more effective, and therefore the science got corrected, right? Um, in pseudoscience, what you'll often see is that not only are there loopholes that keep you from falsifying the claim, an absence of correcting when there is evidence that's contradictory, there's an emphasis on confirming instead of falsifying, which is really a non-scientific approach. Going and looking for things that confirm your belief to begin with, rather than being skeptical, rather than being objective, or as objective as you can be, and trying to control for bias as you would in science. There's also a tendency to place the burden of proof on the skeptics. That is not a scientific perspective on how facts work. The burden of proof is always on the person or the group making the proposition. It is not on the skeptic to bear the burden of proof. We assume that the theory is wrong until we see sufficient evidence. This is like the Socratic method, right? Your opinion or your view of whatever doesn't hold a lot of validity if it doesn't stand up under questioning, and that's your responsibility to be able to defend it from such questioning. Excessive reliance on testimonial evidence. We might think of testimonial evidence here as being synonymous with anecdotal evidence, right? Not looking at the hard numbers of large samples of data, but rather really focusing on individuals and their anecdotal experiences as evidence, which is not what we think of when we use the terms scientific evidence. Evasion of peer review, right? Part of the self-correcting process in science is the peer-reviewed journal system, right? The idea that if you're going to publish your findings, you have to include everything. You have to show not just your results, but your methods, and you have to explain how you arrived at the variables you're measuring and how. You always have to include a section that gives a review of previous research that shows how you reasonably arrived at these conclusions based on what came before you. You know, we're always standing on the shoulders of giants, so to speak, in science. So pseudoscience will evade peer review. It will publish in non-scientific journals. They'll refuse to provide all of their data, but simply just present the results or even just the interpretations. And when pressed, they will not be able to stand up to basic scrutiny of the traditional science process of peer review. I already alluded to this a moment ago. The literature review in every journal article, you have to sort of show the research that precedes your research and how you arrived there. So there's an absence of that connectivity in pseudoscience with existing scientific thought. It just sort of bursts into the scene. It doesn't naturally derive from all of the scientific research in that field that came before it. It's just kind of, exists on its own in space and doesn't really have a connection to the rational thinking process and research process that's gone on leading you up to this point. One of the things that pseudoscience does to cloak itself in the veil of science is an overuse of impressive sounding jargon. This is an example that I will think of because I feel pretty safe in doing this. I've done a fair amount of my own research on this topic, but I'm going to pick on Scientology for a moment. It calls itself Scientology, right? It's right there in the name. It makes a lot of pretty ludicrous claims about reality and history and science in general. But they are, L. Ron Hubbard was a world-class grifter. I mean, a really, really classic world champion level con man. And he was also a very prolific writer. He wrote tons and tons and tons of science fiction pulp books as a career before he founded Scientology. And he was very facile with language, and he had enough understanding of science to incorporate a lot of impressive sounding terminology. One thing you often see in science too, one thing you see in pseudoscience is what are called neologisms, made up words, right? Words that are created for just that particular area that are not derived from the normal vocabulary of science. Therefore, it's very difficult to have a reasonable conversation to criticize because they're utilizing a term that doesn't really exist outside of that pseudoscientific belief system. And then finally, a failure to specify boundary conditions or settings under which the claims don't hold. This is, again, a way to limit the falsifiability and emphasize confirmation instead of falsification. Essentially, there is no hard and fast rule for when you're dealing with pseudoscience. These are all sort of guidelines for looking at it. But the more warning signs that are present, the more of these boxes you can tick on this bullet list here, the more likely it is that what you're dealing with is pseudoscience and not science. We are very susceptible to pseudoscience, and we're going to talk about that in the next slide. So, as I mentioned earlier, we have these everyday heuristics, these everyday ways of knowing things, this common knowing process. That's normal. That's part of the way our brains work naturally. We rely on personal experience. We rely on anecdotes. We use mental shortcuts, and we do this all the time to make everyday decisions. How do we spend money? Whom do we trust with friendship? This is all things that we're doing all the time. We're utilizing this type of decision-making process. Unfortunately, as we mentioned, that introduces the possibility of a lot of bias. And this is the reason why we are susceptible to pseudoscience, because it will present itself in such a way that it appeals to our intuition, that it appeals to anecdotal evidence that we've observed. So what we'll do is we'll hear that information and it will line up with a way of knowing things that we're very familiar with, which is this sort of intuition or anecdotal based way of thinking. We are prone to something, a very strong bias we all share is called confirmatory or confirmation bias. And this is a natural tendency of the human mind to actively seek out and assign more weight to evidence that favors existing beliefs or expectations. I would really direct you to go check out the Dunning-Kruger effect. You can just look it up on the internet. It's become very popular recently. The Dunning-Kruger effect is a social psychological theory that essentially says the less you know about a subject, the less you actually know about a subject based upon your own education and research and reading and exposure, the harder it is to convince you you're wrong. The less likely you are to hear and integrate alternative evidence and change your opinions. Let that sit with you for a moment, because that is a really interesting concept. What that means is that people, and the inverse is also true, people that are extremely educated on a subject, when presented with contradictory evidence, are more likely to adjust their beliefs and change the way that they view that subject. They are more likely to integrate that information and adapt and adjust and be willing to let go of things they hold to be true. So the Dunning-Kruger effect is very closely related to the larger concept of confirmation bias. One way you might think about confirmation bias is you'll find exactly what you go looking for. There's a proverb that says you'll find exactly what you go looking for. That is why we form our hypotheses a priori, right? That is why we try to control for biases and other confounds that can introduce themselves into our research, because we know that we are more likely to pay attention to things that line up with what we already believe, and therefore not change those beliefs because we miss the evidence that's contradictory. We don't give it as much weight. We don't pay as much attention to it. There is a concept from clinical psychology called cognitive filters. A cognitive filter is sort of a way of filtering information as it comes in through our senses or in our cognition to confirm something that's already in place. And we typically talk about this in clinical settings in terms of depression. People who are depressed tend to have a negative cognitive filter, right? A lot of modern cognitive psychologists are going to define depression as negative thoughts about yourself, the future, and the world around you. So when I then take in information through media, through my experiences, through the world around me, I will be more, if I'm already depressed to begin with, I will be more likely to give attention to and weigh higher evidence that confirms that viewpoint. When I see bad things happening on the news, when someone says something to me that's critical, when something bad happens in my life, I'm going to laser focus in on that information, pay a lot of attention to it, ruminate on it, and allow it to reinforce that belief, those negative beliefs I have about the world around me, myself, and the future. contradictory evidence, someone giving me a compliment, being successful at work, positive news in my world, or some form or another, good news of some type, whether it's in the media or just in my own personal life, I am going to typically be more prone to disregard that information. Maybe not even be aware of it, but at least to discount it, to cut it down, to immediately question it, and not give it as much weight in my judgment. So we all have this confirmation bias in a variety of ways. So as we talked about Popper's demarcation doctrine, his falsification doctrine, I think it's probably an easier way to think about it, centers on the idea that scientists should always try to disprove instead of prove our hypotheses. We want to throw everything we can at that hypothesis to disprove it. If it still holds, then we begin to give it more weight. We have a sense that it might be more valid. So confirmation bias, confirmatory bias is a central threat to science. It is why we always have to be mindful of ourselves and what we bring to the table in our research. And that includes everything. Our mood, our physical state that day, our culture, whatever it is we're bringing to the table, our experiences, we have to be aware of how that influences us and introduces subjectivity rather than objectivity into our scientific endeavors. So your book labels science as what they call uncommon sense. If common sense is these older, more primitive ways of thinking, like, anecdotal experience, intuition, authority, if that's how we commonly know things, then science is a way of uncommonly knowing things. One of the ways that Popper talks about this that I wanted to come back to for a moment is the example. He says that only a single black swan is necessary to disconfirm the theory that all swans are white. Right? We want to pay close attention to things that are falsifying our theories. In contrast to this sort of common sense, this uncommon sense, this scientific endeavor is seen as a way of combating pseudoscience. It seeks to self-correct. It aims to falsify our theories rather than confirming them because we want to get to something that is more valid. We want to try and strive for accuracy in our understanding about the world around us. Okay, that will cover it for Chapter 1. I will see y'all in the Zoom meeting and we'll talk more about it.